next speaker is Deisy Fernandes. Deisy is the Presidential Diversity Postdoctorate Fellow in Chemical Engineering at Brown University. She started her undergraduate studies in Brazil at the University of Sao Paulo and finished her BS in Chemical Engineering at UIC. She received her PhD in Chemical Engineering at the University of Illinois at Chicago in June 2015. She loves working with nanomaterials for 3D printing, nanotechnology, and biosensing. She has a long list of awards that I won't go through, but great job on those. She's passionate about outreach, working with underrepresented groups. She has a lot of accolades, and we're just so glad to have you here, Deisy, and take it away.
Thank you. Can you see my screen?
Yes, ma'am.
Great. Okay. So currently a presidential at Brown, but I'll be talking a little bit about the work that I did during my PhD at the University of Illinois Chicago, and also part of the work was done at University of Bordeaux at a center Pop Pascal in France. Graphene MoS2 gel for aligned 3D printing for electronic and mechanical study. So trying to understand a little bit the background and why we did this research is the idea came as if your light bulb breaks at home. Could be that if you could just go in your computer, 3D design a light bulb and 3D print at your house, and the same idea would be for solar panels or other electronic devices. More, we saw on 3D printing full houses, right? So this house was 3D printed just under 120 hours in Europe, but now we have a huge complex in Texas that was fully 3D printed. There's just so many different applications for 3D printing. Why don't we try to create something where we would have the blocks made out of graphene and some other conductive material, energy storage with the same way, having the cables and everything already 3D printed. So that's really the goal in the future where we want to get, where we could implement those of the house also on the 3D printing process, where the whole house would be fully 3D printed. So which materials did we use and how we use it and what it's going to be. Is I want to talk a little bit about the materials, the process, and how we use the 3D printing. And the 3 studies that was done was the mechanical, Raman is about the and electrical analysis printed structures. So the material that I used was the first one that we started with was graphene. We were buying this filament. So graphene was, for whoever is not familiar, in 2004. On the image was just a honeycomb, and is nothing less than if you separate the layers of graphite and you come to just one thin layer of the graphite, that is actually what graphene is. So really interesting is because thin that the conduction happens in just 2 directions, so just X and Y. That's why it's called 2D nanomaterials, because we don't have that 3rd dimension, and that brings a lot of and fight. So even though once we stack the graphene together, what we want to try to create is have this 3D printed structure with graphene, but do not properties of graphite. Having now these amazing properties that is a super capacitor, can be used for LED lighting, it can be used as a sensor. There's just so many applications that graphene can be used for, but a lot of that is lost to go to. That's what we're trying to get. We're trying to get these 3D properties of graphene with a larger devices. We bought, and we were able to 3D printed structures that was conductive and would had some properties. But when we're buying the filament, there's a lot of not just PLA but other materials. Of course, the company did not. And so the idea was to try to find a way to make the materials ourselves. And once we try to figure that out, we also try to think, okay, which other can we use besides graphene? We had two other materials to the research. One material was mobilium disulfide. MoS2 brings the semiconductor property. So graphene is always conductive. It needs a little more. That brings the on and off switch of electronic applications. So if we're thinking about not just electronic components of the house, but if you think of electronic device, your cell phone, you always want to turn on and off. So MoS2 would bring that. And bottom nitride would bring the insulation capacity. So bottom nitride, if you think about a cable or something for your device, or in the case of the electrons to be confined inside of that cable. So the bottom nitride would bring that property to it. So how do we actually do that is time, tissue scribe 3D printers and all of that. We didn't have any of that. We didn't have money for that either. And part of Grow was they could pay for me to go to France, a professor there. He modified a 3D printer to 3D print with a syringe. So we made the gel, we mixed the graphene and MoS2, and we 3D printed that. And after we doing lyophilization. So the first part of the process was mixing graphene and MoS2. We use a TIPE sonicator that's done a lot already with many different. But the interesting thing is that what a lot of people do, especially for graphene gel, is supercentrifugation. Once we use graphene and MoS2 with the difference of density, we have the phase, and that meant that the supercentrifugation anymore. So we had to find a different way to concentrate the solution and create the gel. So when we're starting, we have this graphene solution for 8%, extremely low concentration, so we have to increase that a lot. And the idea that was done for some carbon nanotubes was like over here. So on here, as you can see, this on this vial over here, we have dextran solution around it. Dextran will remove the side of the membrane, concentrating our gel and creating the gelation of our material. The problem is that I had just 3 months in France. I didn't have spend 1 week to just obtain one gel. So the first novelty of our process was using this absorbent gel, where we cut the time to about 4 days for some of the materials, and some of the materials I was able to obtain in under 2 days, as you can see here in the bottom. So this was the first novelty, and from the first day we could already see the liquid crystal phase of graphene. So this is the same material day one, angles, and really showed that the material was made from day one, and we were able to make a different concentration. So this is starting from just graphene and to 90% to 10% of graphene. So how the MoS2 was used in powder. So this was great. And even though the MoS2 was bulk, we still were able to mix it well and obtain the gels. Obtain this different concentrations of gel, we have to understand a little bit of the rheology. So Leanne just went over a lot about, so I won't go into much details because she did a great and a lot about we did here on this, and what I want you to get from here is really just how the material behave and how we proved that this was actually a gel from using the. So there were 2 points. So in our materials, our gain modulus was always above the loss modulus. What it means that for all our materials, we actually obtain gel. And what was really interesting too from our material was it was viscoelastic. From this graph of the flow sweep, the material went back to its original property almost every single time. It went almost to the same point it was before. It was really close to all of that. Could you see that viscoelastic? So After that, we had the rheology done for all the different concentrations of graphene and MoS2. And why do I really talking about the rheology of that is because there were two different ways to figure out the alignment of the printing. So we could look at the crossover point between the G prime and G2 prime, or in the Hershey-Buck. So doing those two methods, we had to ensure that the pressure that we were printing was above of the shear yield stress. On the videos, if it shows, I'm not sure if it's showing. Okay, so as you can see here on the video, there is a black part on the 3D printer, and black part over here is just a sensor where it measures the pressure as you're printing it. And this pressure was really important to prove that we're actually having the alignment. So in chemical engineering, when we learn about flow and plug flow, to ensure that this shear yield is fast. So we did that for all our samples, and we were able to 3D print all the different samples. So this one that is showing here, the hollow cylinder printed, was done for the mechanical stress. That was the first study that I did while I was still in France. So here, what is happening is we're just pressuring it and measuring the tensile stress, and with that we vary the different concentrations of MoS2. And what was really interesting, as you can see, as we increase the amount of MoS2, we also increase the modulus, meaning that it becomes brittle. So we did all the mechanical stress, and that makes a lot of sense because of MoS2 and all the water. So we did lyophilization, we dry the sample. So the sample a lot of water in it, remove it, have all the porosity that becomes easy to kind of crush it as we're doing the mechanical stress, and the material do not return it at all because of all the porosity. After that, I brought it back and I did the Raman study. So what is Raman, for people who are not familiar with it, is a laser that uses phonons. So the phonon shines through the sample, and when it shines here on the bottom of the sample, the material will vibrate either in plane or out of plane. And once the phonon returns back, this detector will give a specific picture. Those are kind of the fingerprints of. So this is done for graphene, and in our case, I had MoS2 and graphene oxide because I did lyophilization, the freeze. I also oven for oxidizing, so I had reduced graphene oxide, and after the reduction, we don't have that third peak that you showed before. So as you can see here, mostly MoS2, the peaks of MoS2, and in this case, show the peaks of MoS2 and graphene oxide. So why was this study important? Why am I talking about this vibration? Once we want to learn about the electrical characteristics of it, we need to understand how big those graphene sheets are. And using that data, we can obtain the average size of the graphic region. Those is about 8.3 average that we got from our samples. And another thing that was even more important in this case, looking for all different samples. And as you can see here, we don't need the MoS2 in this case because we have concentration of MoS2. As we increase the amount of MoS2, you see the peaks throughout the whole device. And those scans is done 20 microns apart. So every line you see is from the sample going 20 microns in depth as we're scanning those samples. So as you can see, all of this show all the characteristics for all the material that we have. We can obtain concentration. Value means how many free electrons do we have flow to be able to flow on this device. And this was really important for the electronic applications of our devices that we wanted. farther, and we use a cryostat, and we have the electrodes connecting in the two ends of an electronic device. And once we connect those two ends of it, and we the current voltage from going from 17 Kelvin to 200 Kelvin. Sorry, I should have a unit here of the temperature. So this is varying temperature, and we have actually using the heat, we can thermal barrier. So this AA over here is how much energy we need for the electrons to start flowing. So this value is a little bit higher as if we have just graphene is 16.24. For the graphene is about 8. So that means that we need a little bit more energy for the electrons to start flowing. That really semiconductivity that I mentioned before, the on and off switch that you would need for the electronic application. And the other thing that we can do with the same type of electronic study is doing the following equation, and that is here, this A naught is the average tunneling distance, is how much distance you have between one graphene and the other. And to try to understand this 0.45 nanometer, it's really important to determine if the electrons are hopping or tunneling through. And the data that we get here is really what is really important for us in this case. So as you see here, we have a graphene sheet here, and we have another graphene sheet. So the 0.45 that I mentioned is nothing more but the MoS2 distance that we have in between one graphene sheet and the other. So the electron is coming here, and it needs to tunnel through the MoS2 in order to use that. So the MoS2, it tunnels through the MoS2 and go to the other graphene. So this is really trying to understand the electronic characterization. And the other thing that we had in this study was the 16.20 energy for the electron to start flowing and tunnel through the material. So as a conclusion, as you can see here on the picture, there were larger printed. We were able to have a graphene structure to printed, and there were smaller devices too, as the electrodes and the hollow cylinders. Was really interesting that we were obtain the different concentrations and we were able to print it with them. As you mentioned, Leanne mentioned before, when we were 3D printed those gels, especially since we're making ourselves, it needs to be liquid enough to be extruded to maintain the shape of extruded. So there's a lot to play around and to be able to have those structures and to have it large enough. In this case, even though it's much smaller than the talk that we had earlier today, it's still large compared to some of the materials that are done now with graphene and MoS2. So we were able to understand, characterize the material, understand the electrical study, and I want to all the agencies that helped me to conclude this research. This is still ongoing. We want to have a lot more research done with graphene MoS2, graphene and bottom nitride, and maybe mixing all of them. I just purchased the more materials now. Those two are my advisors, Vikas Berry from University of Illinois, Chicago, and this is my advisor in France, Philippe Poulon. And any questions now?
Awesome. Thank you so much. That was super interesting. I think we're all looking forward to see what the future holds for this technology. We have a few questions. First one is from Leanne. She says, this is very cool work. Does the conductivity change when you stress the printed structures?
Yes, it does. So I didn't show here even just the filament, the PLA filament and graphene. It changed a lot. So it really varies. And what was interesting, that what actually really affected the most, the part where it was most tensed. So the part where it was most stretched was really what was driving the conductivity of it, the filaments to their printed structures.
Awesome. What are the next steps for tailoring the fluids for more accurate or high resolution deposition?
So the first thing is trying to control better the MO nitride that I've been the TIPE sonicator, the MoS2 and the bottom nitride. When I first did in France, I did not do the characterization there. I did it here, and all of the materials were still bulk, and that influences a lot of the characteristics and the property afterwards. So I'm trying to get them to be well mixed and a few layers and not have them in bulk, because that will really affect the property. So that's probably the first step. And the second step would be to acquire better printers for the deposition part, and hopefully have more money for research to get a better printer.
Awesome. All right. Are there other carrier fluids you've considered that dry more quickly?
Not yet. There's a lot of other materials that I want to work with. Maxines that are coming out. There's a lot of other materials that are still potential for research, but I haven't done it yet.
All right. How might carbon nanotubes affect the properties versus graphene, or would it affect the viscosity, or would the effect on viscosity be too significant?
So it really depends on the application that you would want. The applications could vary a lot, especially, for example, one of the applications that we want to get after is actually having materials intercalated. So if you think about it, like virucidal or some other materials that you want to try to create that and still have that surface slowly releasing some material, the carbon nanotubes wouldn't be able to hold as much as graphene, as this graphene would be just between nanotubes. So it really depends on the application that you're trying to use. For the electronic applications would be the same thing. It would vary on how you want to use that afterwards and how the properties that you want to obtain.
Great. All right, last one. When will you be able to print a simple Blinky with an LED circuit? I guess a blinking LED circuit is what they're asking.
Yeah. I'm not sure. Hopefully soon. We're behind on that. My first goal is to have the energy storage. With the graphene MoS2, MoS2 is really, you can emit light with it, but it's not able to see it with the detector, but not with naked eye yet. So hopefully, if we can create something that we can really detect it, that light emission from MoS2, we can actually get to that point soon. So we'll see. I'm working on it now. Hope we can get that soon.
Awesome. Well, thank you so much for this very interesting talk.